Swayam Prabha. Digital India. Educated India.
Good morning. We are now starting lecture 17. This is our first session on module 3, basic matrix methods. We have completed the review of basic structural analysis. We took 16 hours, 16 lectures to finish it. And the reason why we spend so much time is you really can't do anything advanced unless you're strong in the basics. And that's a continuing problem we face with structural engineers. And I think it's a very good idea to always go back to the basics and strengthen them. So this is module 3, basic matrix concepts. We will first cover simple mathematics, principles of linear algebra, which you probably already studied. So it's a quick review, and then we'll get into how you can apply concepts of matrices to do structural analysis. The book we will be following is the book I have written called Advanced Structural Analysis, published by Narosa in India and Alpha Science International. It's a hardbound edition abroad. The topics covered in this course will be, after the review of basic structural concepts, will be matrix concepts and methods. Then we look at how to apply these concepts to structures with axial elements like trusses. Next, how to apply them to beams and grids. Next, plane and space frames. And finally, in the 7th module, we will be covering a bit of nonlinear analysis as applied to elastic instability and second order analysis. In this particular session, where we cover the mathematics underlying matrix concepts, we will review what we mean by a matrix, a vector, the elementary matrix operations including matrix multiplication and transposition. We will look at what it means to know the rank of a matrix and how it is useful in solving linear simultaneous equations, which is what we need to do in structural analysis, and how it can be done using matrix inversion. And finally, we look at eigenvalues and eigenvectors, because they have a role to play, especially when you do elastic instability analysis and later in dynamics. But before we do all that, we should see the role that matrices play in structural analysis. Why do we need to study this topic, which you had studied in mathematics? How does it have a role in structural analysis? Could someone give an answer to that question? Because structural analysis is all about finding the response, the force response and displacement response of a given structure when it is subject to a given set of loads. The loads could be direct loads, direct actions, or indirect loads, including support movements, environmental changes and construction errors. So where do matrices come here?
We can build up matrices for one load to the other points at the location, and we can build the matrix for different position, different forces. What would be the reaction for these forces?
Okay. So now we are actually stepping back from calculation and trying to look at the big picture, because if you want a digital computer to do structural analysis, you have to see the big picture, and you realize that basically you are dealing with numbers. If you want to find unknown forces, internal forces, bending moments, shear forces, axial forces at different locations, you are actually dealing with numbers which can be put nicely in arrays. Okay, so you are dealing with vectors and you are dealing with properties of the structure like the stiffness matrix and the flexibility matrix. So that is how you can deal with it in a matrix configuration. For example, from the input side you definitely have the load vector, which are loads that are applied at different joint locations. You may have known support displacement, so you have a support displacement vector. You may have some initial deformations or temperature changes, and what you need to find is the displacement at all the degrees of freedom that you have identified, the active coordinates. You need to find the support reactions, you need to find the internal forces. You may also want to find the member deformations, like the elongations in truss members. In short, all the variables, all the quantities that you need to find in the force field and the displacement field can be expressed in a numerical manner, but you need to conveniently do it, and you need to do it in a systematic way. And if you want a computer to do it, you also need to first model the structure itself, which is not that easy. That means you and I can see a truss and visualize it, but how does a computer do it? Well, the computer does not think, so you should be able to even define the geometry of the structure using coordinates, Cartesian coordinates, and you need to also check whether what the computer interprets is the structure that you have. Please note you are dealing with a mathematical model of an idealized structure, and in modern software packages you have a tool, a visual ability where you get back the picture of the structure that you input, and if you find some members are out of place or oriented the wrong way, you can make corrections. So you can use Visual Basic, for example, to do such things. That is a separate field. So basically you have some unknown quantities and some known quantities in the displacement field and the force field, and you need to know certain laws which are hidden in the structure, which enable transformations to take place. So basically we want to transform the loads to the responses, and this becomes easy, relatively easy, when you are dealing with a linear analysis, because it is a linear transformation. You are actually converting one vector to another vector with the help of a matrix. For example, one of those sets of relationships are, as I have shown there, relating forces, the force field to the displacement field with the help of the stiffness matrix, which you can partition. And you have a large number of analysis software packages available today, and unfortunately today we are in a stage where structural engineers are no longer doing any manual analysis, and they are learning how to use the design or the analysis manual that comes along with the package, and you input some numbers and you get some output, but if you really do not know what is going on, it is garbage in and garbage out. In fact, if you read the preface to this book on advanced structural analysis, I have raised some of these concerns. In the olden days, when there were no computers, there was no choice, you had to understand structural behavior. You had to know you have to know whether the bending moment that you calculated makes sense or not. You have to know whether it should be sagging or hogging, but now you do not know, because you are getting some number thrown up by the computer, and the need to do analysis faster and quicker is so strong now that there is no time to pause and reflect, and that old breed of structural engineers who really understood what was going on is a vanishing species. So it is important to always step back, to have some rough checks, which is where you need to have a good foundation of basic structural analysis. So here is the first sentence in the preface. There is an increasing tendency among modern structural engineers to lean heavily on software packages for everything. Okay. In fact, even design is done without thinking. You have computer aided design. At the press of a button you get big reports which the client receives and thinks you have done a phenomenal job of, but actually all you did was to press a button. And in fact today we have reached a stage where quantity surveying, planning, everything is programmed. The only thing the computer has not yet been able to do is actually construct buildings at the press of a button, but maybe that may also happen and hopefully the building will stand. So this induces a false sense of knowledge, security and power. The computer is indeed a powerful tool and an asset for any structural engineer, but it is dangerous to make the tool one's master and to make it a convenient substitute for human knowledge, experience and creative thinking. So I hope you appreciate this. I hope you enjoyed what we did in basic structural analysis, but you must not lose that touch and always go back to it and have simple ways of checking your answers. So that is where matrices come in. So let us quickly cover the mathematical concepts. What is a matrix? Now you should think general, because matrix concepts can be applied to a wide variety of not just engineering issues, but even issues in biology, in social sciences, economics and so on. So what is a matrix? Set of things. There are no things. Computer doesn't see things.
Set of numbers.
Right. By definition, a matrix is a rectangular array of elements arranged in horizontal rows and vertical columns. So it should look neat. Okay. It should look neat, and every number has a place. Aij, ith row, jth column. So it is a rectangular array. So I wish you had said rectangular, you did not say it. It is not a circular array, it is a rectangular array. The entries of a matrix are called elements. They are scalar quantities, they are not things. They are commonly numbers, but they can also be functions, they can be operators, they can also be matrices which are called submatrices, and they could be algebraic functions, but they should make sense. So you have mathematics and you have physics, and our job is to link the physics to the mathematics. Every number has a place and a meaning. So typically there are many ways you can write or designate a matrix. In textbooks you will find usually with a bold capital letter. Okay, so A is shown bold, but when you do it on paper you can't make it bold unless you have the bold ballpoint pens. So you have to, what we normally do is we put braces outside it, box brackets commonly as shown here, and there are alternative ways you can do it, but actually that one letter can stand for a huge set of numbers, variables which can occupy numerical values as shown here. Now what is m into n? M rows and n columns, that is called the order of the matrix. So you know very well, it is called the order of the matrix. So let us see, when m is equal to n, what do you call that type of matrix? Square matrix, very good. When all the elements are 0, null matrix, it has a symbol capital O. Okay. When the off diagonal elements are 0 and all the diagonal elements are unity, it is an identity matrix. Very good. Now these are, so we can go fast because you seem to know everything, but at least you know you should know the notations used. For example, a 3 by 3 identity matrix looks like that. What are these elements called? You have two diagonals in that matrix, you have diagonal the other way, but there is a principal diagonal. Okay. And a matrix which has non-zero elements only in the diagonal is called a diagonal matrix. Very good. Is this a diagonal matrix? No. So how would you, what are the different adjectives you can give for this matrix?
Symmetric.
By the way, a stiffness matrix looks like this. Typically a stiffness matrix looks like this. That is why I chose, so it is symmetric, very good. What else? It is square, very good. Can a non-square matrix be symmetric? No. So symmetric necessarily includes, is it an upper triangle?
No.
All the diagonal elements are positive, that's true. But what's the name of the matrix? I am not asking you to describe the contents of the matrix. This can be any matrix. In structural engineering, it could be a stiffness matrix. It's a banded matrix. Okay. Because why is it a banded matrix? Because you have only the diagonal elements and you have elements next to the diagonal, so it forms a band. That's good. It's a banded matrix, and many of the elements are 0. There's an advantage in terms of storing the matrix if many are 0. Why? You can store only the banded portion. Okay, so storage is easier. That's called a sparse matrix. So square matrix, symmetric matrix, banded matrix, sparse. Sparse means not filled, empty. This class is relatively full, but on the days before you have other exams, you have a sparse matrix here because some of you don't show up, right? So now it's not sparse. What are these matrices called? Very good. Lower triangle typically shown with capital L and upper triangle shown with U. And you are familiar with partitioning of matrices. When do you need to partition matrices? When you want to make life simpler. When you deal with a complex system, you want to operate with subsystems. You don't want to look at the big picture all the time, but so you pick out little pieces from your big picture, but you should know where it is, how it is positioned and so on. But always, so you can draw these partition lines and subdivide, and you have different sub matrices will have different orders, but they should all add up to the order of the full matrix. Quickly, you seem to know everything about matrices. What about a vector? Is it a type of matrix?
Yes sir, it is a matrix.
Which is bigger, matrix or vector? Matrix. Which is more general? Matrix, right. So vector is one type of matrix. What is a vector? It's a column? Okay, it's a matrix which has only one column, right? A vector is a simple array of scalar quantities typically arranged in a vertical column. Hence, the vector can be visualized as a matrix of order m into 1, and you don't use the word order anymore, you use the word dimension. Okay, m is the dimension, and you can say elements, but the right word to use is components. You have components in a vector and elements in a matrix. You have dimension in a vector because the one of the other order items is equal to unity, and you have an order in a matrix. Okay, so it's typically arranged like this, and again you have a bold letter to describe the vector, but here the brace we use just for convenience is a curly brace, but if you put a square brace you are not really making a mistake because it is after all a type of a matrix. But don't put a curly brace on a matrix of size m into n where n is not equal to 1, but you are allowed to put a square brace even for a vector. When you have something like this, some people call this also vector, but it's actually the transpose of this that is a vector. So this is sometimes referred to as a row vector, but it's strictly not a vector. Now vectors are important, you know, we are dealing with displacement vectors and force vectors, so they have some meaning, and it's good to see the background. We can visualize a multidimensional linear vector space Rm whose dimension m is given by the minimum number of linearly independent vectors with real components required to span the space. These are beautiful words. There is a word called spanning, there is a word called linearly independent vectors, there is another word called basis. What is basis?
Because we can span this.
Sorry, one at a time. Yeah.
Linearly independent vectors, we can span this.
Okay, what's the why do you need to get a basis? Okay, do you see it has a role not just in physics but in other fields of knowledge? let us take social sciences. In fact, it is more difficult there because if you really want to get a complete picture of say human behavior, you need to be able to construct a framework where you have these linearly independent vectors, and it is very difficult because you have to establish that they are independent, and that provides a framework for you to describe behavior. So these are not just mathematical terms, they have wide applications, and so vectors are said to span a vector space if the space consists of all possible linear combinations of those vectors. So you should be able to capture any vector in that space with the help of your linearly independent vectors, and any set of vectors that are linearly independent and also span the vector space is called a basis of the vector space. What is the simplest basis that we use in physics, for example? IJK. So in a 3-dimensional space, you are familiar with this, you have IJK and you have unit vectors which form a good basis. So you have 1 0 0, 0 1 0 and 0 0 1, and any vector in that space, for example 2 minus 1 3, you can write it in a column, but it actually has a sense of direction, v equal to 2I minus j plus 3k, and it also has a length which is obtained by the resultant of the scalar quantities, right. So you are familiar with it, it is also called the magnitude. Is it clear? So vectors are meaningful, and a set of vectors v1 v2 to vn having the same dimension m is said to be linearly independent if no linear combination of them other than the 0 combination results in a 0 vector. That is the proof whether you really landed up with linearly independent vectors, otherwise you have a problem because there is a correlation between vectors. Elementary matrix operations, I will go very fast, you are familiar with it. You have scalar multiplication, the scalar is never shown in bold, so lambda is a scalar. You have matrix addition, and a plus b will be equal to b plus a, that is a property. What is that property called? Commutative property, and if you put a negative sign, so we only say addition, but addition is generic, it includes subtraction because you are putting a multiplying with minus 1 which is a scalar. Matrix multiplication is, when you studied it first time, it looked very funny because it did not look like the multiplication of scalars, but now you are used to it. So you have a distributive property also, a plus b plus c is the same as a plus b, which is a matrix plus c. Okay. Now ab equal to c, you can't just multiply any two matrices, right? You have to satisfy some requirements. What are those requirements?
Second one.
So basically you know what to do. If you want to find Cij, you have to take the ith row of the A matrix and the jth column of the B matrix, and you have to multiply each term with its corresponding term. So they must match in terms of dimension. So that is why m into n order multiplied by n into p order will give you an m into p order, right. So you are familiar with this, but let us look at it more closely. You know how to do it, but let us see if we can make some physical sense out of it. I will give you a clue. Okay, you can do that multiplication in this manner. What does this manner suggest? Now this is something you may not have studied when you did linear algebra. What does this signify? Right, I can get the same answer by doing the multiplication in this way. What does this suggest? It suggests a certain principle. I took the first column, I took the first element of the first row, I took the second column, I took the second element of the first row, and I get the first column in the resulting matrix. So what does this principle show? Linear combination of, very good, every column vector of C is a linear combination of the column vectors of the pre-multiplying matrix A. Okay. Incidentally, in terms of direction, if you multiply a vector with a scalar, you are getting the same direction, you are only changing its length. You can do another operation in the other direction and you will prove that every row vector of C is a linear combination of the row vectors of the post multiplying matrix B. That is just a physical meaning to so the moral of the story is you can blindly do matrix operation, but you can also do them with your eyes open and figure out everything makes sense. You are playing with vectors and you have these properties A, B. What are these properties? You are familiar with all of them. Associative and distributive, and then if you multiply with a null vector you get anything multiplied with 0 is 0, and you get identity only replicates. The commutative property is not there, you are familiar with it. AB is not equal to BA, you may not even be able to do the multiplication sometimes. Okay. Transpose, you are familiar with that. Transposition is an operation in which a rectangular array of the matrix is rearranged or transposed such that the order of the matrix changes from m into n to n into m, with the rows change into columns, preserving the order. So if the original matrix A is Aij, then the transpose will be Aij transpose, which is Aj, and the order changes from m into n to n into m. You are familiar with this, and you have these properties. If you take the transpose of the transpose, you get back the original matrix. If you pre-multiply it with the scalar, you can take it outside, and this is interesting. The third one is also simple. A plus B the whole transpose is A transpose plus B transpose, but AB the whole transpose is B transpose A transpose. So here you have to do a switch, then only it works. Supposing B and A are the same, okay, then what is the kind of matrix that you get? If you multiply a matrix, pre-multiply a matrix with its own transpose, what is the type of matrix you will get? You will get a square matrix plus, it will be symmetric. How do you know it is symmetric? You take the transpose of this matrix and you will get back the original matrix. So that is very interesting, okay, and you can demonstrate it with examples, we will not spend time. Sometimes you see matrices where the transpose gives you a negative sign, okay, so this is called a skew symmetric matrix, right. So now next we will talk about the products of two vectors. You can't multiply two vectors, you know that. Why? Because they both have this, you have to take the transpose of one of them. You commonly meet this situation when you want to find work. Take in structural analysis, you have the force vector, you have the displacement vector, you can't multiply F into D. Either you take the transpose of F and multiply it with D, or you take the transpose of D and multiply it with F. Is it clear? Then you will end up with 1 by 1 quantity. What is that? That is a scalar. It's a scalar. So the product, what kind of product is this? Well, we say dot product in physics when you deal with 2 and 3 dimensional spaces, but it is called an inner product in general. It is called an inner product, and you can also show it in this fashion. This is a symbolic way of showing the inner product. So I will read this. The product F transpose D equal to lambda results in a matrix of order 1 into 1, which is nothing but a scalar. Such a product, which is sometimes denoted as F comma D with those triangular braces, is called inner product or dot product in vector algebra involving 2 and 3 dimensional vectors. This product essentially reflects the projected length of one vector along the direction of the other vector. We are familiar with this in physics. The magnitude of any vector V can also be viewed as an inner product of V with itself. You are familiar with that. Vectors are said to be orthonormal when, if you do their inner product, you either get 0 or 1. Okay. What is this symbol called? This delta is called the Kronecker delta. Okay. The commutative product of the commutative property of the inner product is what I explained a while back. You can calculate work either by converting the force vector to a row vector or the displacement vector to a row vector, you get the same answer. And if you introduce the relationship between force and displacement through the stiffness matrix, you can arrive at an interesting conclusion. Can you tell me what that conclusion is? See, the first is the commutative property, the second is a stiffness relationship, it is a law. If you plug in the second property to the first property, what can you end up proving? K is, yes, that is really good. So you take the inner product in this manner, you get lambda. Now you substitute you take the transpose of this, you still get lambda. Then when you compare these two expressions, d transpose kd is the same in both, but in one you have k transpose, so you end up proving k is equal to k transpose. So it is a very elegant mathematical proof requirement of why the stiffness matrix must be symmetric. Okay, we will study symmetry from the structural analysis point of view later. Now let us get to the real need for bringing in matrices. We need to solve equations, right, and we want the computer to do it, we do not want to do it ourselves because it is a pain sometimes. So linear simultaneous equations can be written as Ax plus Ax equal to C. A is called the coefficient matrix, as we saw in this case of the stiffness matrix, it is a property of the structure. X is a vector like the displacement vector, and C could be a load vector. C is some set of constants, right. If C is 0, well, you should not say 0, you should say O, because 0 is a scalar, O is a vector or a matrix. Then those set of equations are called homogeneous equations, you are familiar with them. When do you need to look at the solution for homogeneous equations? In solving linear simultaneous equations, even if you have a non-zero C, a constant vector, you may still need to inspect this solution. That is called the null space of A, all possible solutions. When do you need to do this? It is very interesting, though we do not directly need it in structural analysis. You need to do it because well, it is related to what is called the rank of the matrix. What is the rank of the matrix say? It is a beautiful concept.
Independent, number of independent we can find out. Number of independent.
Okay, you kind of vaguely know what it means, so let us explore it. Okay, rank of a matrix. The rank of the matrix A is equal to the number of linearly independent column vectors of the matrix, and this number is identical to the number of linearly independent row vectors. So the maximum value of the rank R of any matrix of order m into n is given by either m or n, whichever is lower, and the minimum value is 1. Okay, let us look more closely at this. The subspace in the vector space Rm containing all linear combinations of the independent column or row vectors is called the column space or row space of A, and this subspace has a dimension equal to the rank R. So you have to finally get to the number of linearly independent vectors. Take a look at this matrix. It is a 4 by 3 matrix. Obviously the rank cannot exceed 3. So is the rank 1, 2 or 3? 2. Why do you say 2?
Third one and second one.
That's good, that's quick, smart looking, but in general it is good to keep quiet and do an analysis before you pop out with the answer. 3 you should never say because you can't spot it so easily. Sometimes it is cleverly disguised, you can't catch it, right. So how do you capture the rank of a matrix? So there is a beautiful technique, you have studied this, your MATLAB will do this easily, it is called the row reduced echelon form. relatively easy way of determining the rank of a matrix is by reducing the matrix to its form R through a process of elimination. You are familiar with this? Huh? Yes or no?
Yes, sir.
Now, you need not assert yes. You should have the care and concern for other members of your group. This is a matrix, right? Don't be the dominant diagonal. You should care for those who are saying they don't have an exposure. You cannot insist they have an exposure, right? All you can insist is I know, and that too we'll check shortly whether how well you know it. So it's always good to say I don't know, I want to learn or I want to relearn. Okay. So the idea is, so it's a refresher for many of you. Incidentally, we are just covering the theory, I would say more for fun, because nobody is going to do it at this stage in your life. You are going to press buttons and let the computer do it, but there is a nice story it is telling, and I think it's worth understanding this. So how do we do that? Any matrix R you can finally, through doing elimination. Many of you, those who said no, you are familiar with Gauss elimination. So you basically play around with rows, you multiply and add different rows, you are allowed to do that, right? But you have to do it all the way, including the column vector, right? And so you can play with them, and that's allowed, and you don't lose anything in doing so. You can multiply a row with 2 and subtract 3 from the next row and so on. Those are row operations that you can do, but the idea is you do them so that you can get an identity matrix in the left hand uppermost corner. So you get an I matrix there, and the idea is to get 0 below. So you can always reduce R to this form where you have null matrices at the bottom, identity matrix at the top left corner, and you will get some matrix F. What is F called? It has a name. Those who said you know everything, please answer. F is called the free variable coefficient matrix. Why is it called that? Let's see. It's very interesting. Take a look at this matrix. Okay, let's do it step by step. What's the first thing you should do? Yeah, make what one?
Top left.
Okay,
First
that
layer.
variable. So that's called the pivot. Okay, so you divide that row with 2, and then do a operation and get zeros in the other ones. This can be done. Okay, we'll just go through it fast. You've done it before in Gauss elimination. You would have done this. Okay, next, that's our pivot. You'll get that. Next, you got a lot of zeros already. The top one also should be 0. This ultimate, you've got the identity matrix. Okay, actually the last step is optional when you do simultaneously, because you can do back substitution and get it. Okay, you've got this, then you look at the partitions. You've captured that IFOO beautifully. What's the rank of this matrix? It's the same matrix we looked at earlier. The rank is clearly 2. It's the size of your identity matrix, so it's R into R, that's clear, right? Now this is how you can do it. In fact, you can write a program and it can do it on its own. Rank is 2, and let's look at a set of equations like this. Can this set of equations have a solution? Yes or no?
Infinite number of solutions. Infinite number of solutions.
Infinite solutions. Will they always have infinite solutions?
Yes. Yes.
It may not have.
Rank
It
is
may
2.
not have, because first the constant vector must satisfy conditions of consistency. So it's very interesting, but we don't need too much of it, so I want you to read on your own. I'll just rush through it. You will find, let's look at this. Finally, you have to solve equations like this. Do you agree to this? Those, if you take out those 2 rows, they should look like this, right? That's D0 should be O, and this must be satisfied by C for a feasible solution set. If it's not satisfied, you can't solve this equation. and still you might get infinite solution, that is a different matter, but you can't touch this if you have a violation of consistency. And whenever you have a problem like this, when you have free variables, you have to look at the infinite solutions come from the null space. So you get one particular solution, you must have done this in differential equation. You get one particular solution, then you have to add the null space solution from the homogeneous equation. Okay, let us take a look at this. You have x1, x2, x3, and you have this situation. If you take the row reduced echelon form, it looks like that. Well, the last two rows, the constants should be 0. If you run the operations right through, they will look like that. So you can't do this for any arbitrary c. You agree? Yes. So first that has to be satisfied, then only you can talk of a solution, and then also you may not get a unique solution because the rank is only 2, it is not 3. So first you have to satisfy this, that means you can express C3 and C4 in terms of C1 and C2. So let us look at a problem like that. Let us say C1 is A, C2 is B, then C3 and C4 must necessarily satisfy this requirement. Then you can talk of a solution, but even then you won't get a unique solution because the rank is not full. So let us take an example like this, and you do the row reduced echelon form, you will get something like that. How do you solve this problem? Well, partition it, you can throw away the third and fourth rows because they already satisfy consistency, they are not going to help you. You have only 2 rows, but you have a problem there. So you take the first set of equations, you can write x1 and x2 in terms of x3. Clearly you do not have a unique solution, right. So you take a particular solution, you can choose any value of x3 including minus 342.625, who cares, any particular solution. Okay, for convenience we took x3 equal to 3, then you got a unique solution for x1 and x2, right. But this is not a complete solution, you have to take the null space solution. The easiest null space solution, let us take some scalar like lambda, let x3 be lambda, plug them into those equations, and you will find that if x3 is plus lambda, x1 and x2 must turn out to be minus lambda minus lambda. So what is your complete solution? Right, that is how, this is how you give the, it's for you to learn for your general knowledge. We do not have fortunately such problems except when your structure is unstable, in which case you better worry about the structure falling down rather than solving these equations. You have to make the structure stable. Now the other case we have is when R is equal to n, n is the number of columns which is less than the number of rows. Okay, so coefficient matrix A has a full column rank, but there are linearly independent rows, which also implies that the number of rows exceeds the number of columns. When do you have such a situation? When you have more equations than unknowns, and then you need to satisfy consistency. Again, this comes in unstable structures, so we will just rush through this, you do not need it really. So now it takes this form, there are no free variables here, and the constant still must satisfy because it belongs to the same type. You run this exercise, let us just rush through this. Once you have satisfied it, you get a unique solution. Okay, you do not need to have the null space here, this is the second type, we are not dealing with it in structural analysis. What do we deal with in structural analysis? Case 3 and case 4. What is case 3? R equal to m less than n. When do you get such a situation? When do you get more unknowns and less equations? Statically indeterminate structures. So coefficient matrix A has a full row rank, but there are linearly dependent columns, which also implies that the number of columns exceeds the number of rows. We have more unknowns than equations. It is a situation we encounter in statically indeterminate structures. So now you have only I and F, those O's vanish, okay, you have a full row rank. So your row reduced echelon form looks like that, I and F. So you see you have infinite solutions, but your you do not have to worry about consistency. You do not have to worry about consistency, and so those equations are not there. So since there are free variables present, you have infinite possibilities. So let us take an example like this: Ax equal to c. You run this operation till you end up with the row reduced echelon form. They are consistent, you do not have to check on consistency, but now you well, to make it look like an identity matrix, sometimes you have to interchange rows, you know that operation. You have to interchange rows. In this case you have to do that, and they look like this. And if your constants have numbers like 3, 6, 2, after your elimination they look like 3, 7 and minus 3.5. You solve this, find the particular solution, find the null space solution, and you get, it's similar to the first type of problem except consistency is not there. Okay, we don't even do this. We do it. When did we do it? We wanted to find displacements in statically indeterminate structures after having analyzed it. Remember, there we chose lambda to be 0, so we didn't waste time doing all this. Okay, because you need any statically admissible solutions to apply the principle of virtual work. This case is straightforward, full rank if you are lucky, but if your structure is stable you are likely to get this situation, and if it is statically determinate, this is straightforward. In this case the coefficient matrix A has a full column rank as well as full row rank, and this also implies that the matrix is a square matrix. Such a matrix is said to be invertible or non-singular. And if you have a matrix like this, and all our stiffness matrices for stable structures will look like this, then you do not have a problem. You also have a symmetric matrix in our case. You have a unique solution, and you can use the Gauss elimination method, or you can reduce to a row reduced echelon form and you can get the answer, right. In earlier days we used to make students actually painfully do all this, but today we do not do that. We say you use the computer. Certainly you be familiar with software like MATLAB, where you just press a button, enter the matrix, and how all of you are familiar with MATLAB? There are some freeware called Skylab and so on, but I think we have many versions of MATLAB and MathCAD, so it's very easy today to find the inverse of a matrix. What's the problem with some matrices regarding finding inverses?
Should not be singular.
So that's true. So in structural analysis, where do you see a problem? We'll see that. So matrix inversion. When the matrix A is square and of full rank, an alternative approach to solving the equations is by operation of inversion. X is equal to A inverse C. A into A inverse is A inverse A is identity matrix. You are familiar with these. A inverse gives you back A, and so on. The last property is very interesting. It's like what you got in transpose. AB the whole inverse is B inverse A inverse, and some mathematician gave a beautiful physical feel to this. He gave an analogy. Do you remember? I think I mentioned this earlier. He said, how do you put on shoes? You first put on socks, that's A matrix, then you put on the shoe. How do you reverse the process? You have to first remove the shoe, then you remove your socks, right. So that's why AB inverse is B inverse A inverse. Very easy to remember, very nice analogy. What's the determinant of a matrix? Why do you need to know it? Yeah, whether it's in. So in general it can be proved that the inverse exists if a scalar property called the determinant of the square matrix, denoted A with those vertical lines, or det A or delta A is not equal to 0. For a diagonal matrix, the determinant is given by the product of all the diagonal elements. You know that? That's an easy way to find out. So I think you're familiar with finding determinants, so we won't spend too much time on this. You know about cofactors. Okay, you really don't need to do it in this course in matrix methods, but it's good to refresh these concepts. You know about the adjoint method of finding the inverse? Yes or no? Okay. You know about Kramer's rule?
No.
Okay, so okay, those who said no, and if you're interested, please read a good book in matrix algebra, or just read the second chapter in this book on advanced structural analysis. It's good to browse through these, and we can spend hours discussing these different methods of finding the inverse, like the Gauss-Jordan elimination method, Cholesky. You know, these are very good for stiffness matrices, but we will not do that. Okay, so we will. Kramer's rule you're familiar with. It's very easy to do when your order is up to 3. Beyond 3 manually it's not worth it, and we use elimination methods to do so. We will stop here. We will discuss or maybe we'll finish this condition of a matrix. A matrix, if it's ill conditioned, you are not sure about the accuracy of the inverse that you get. How do you know whether your inverse is right or not? You again multiply it with the original matrix, you should get you will not get, not necessarily, you will have a lot of rounding off errors while you do your elimination, and so unless your matrix is healthy, it's in good condition, and there are tests to check the condition of your matrix, you can't be sure of finding its inverse, and therefore solving you're not sure about the answers you get. Now fortunately for us, our stiffness matrices are all healthy matrices, they're all well conditioned. You know about the property of positive definiteness? Okay, so you should read these. I'll just finish this. A square matrix of order n is said to be positive definite if for any arbitrary choice of n dimensional vector x, the product x transpose Ax yields a scalar quantity that is positive. If it is negative, it's ill conditioned. If it's 0, it's called semi definite. Okay, and you can use eigenvalues to decide this. Basically, if your diagonal elements are heavy and they are positive, you got a well conditioned matrix. That's the thumb rule, and stiffness matrix will be like that. Flexibility matrix, there is no guarantee. That's another reason why flexibility matrix is not preferred for, it's too flexible, you know, you can run into problems of finding the inverse. Thank you, let's stop.